Atoms form the building blocks of matter, each one a tiny system with a dense central nucleus surrounded by orbiting electrons. The nucleus itself holds protons and neutrons bound tightly together by powerful forces. In certain heavy elements like uranium, that balance can be upset. When a neutron strikes the nucleus of uranium-235, the nucleus becomes unstable and splits into two lighter fragments. This split releases energy along with 2 or 3 additional neutrons. Those new neutrons can strike neighboring nuclei and repeat the process. The result is a chain reaction, a cascading sequence in which each fission event triggers others. In a controlled setting, the reaction proceeds at a steady rate rather than an explosion. The released energy appears mostly as kinetic motion of the fission fragments, which quickly heats the surrounding material. That heat is the practical source of power in a nuclear reactor. Neutrons play the central role in keeping the reaction alive. Some escape the fuel, others are absorbed by non-fissile atoms, and still others cause further fissions. Designers adjust the number of neutrons available through geometry, materials, and control elements so the chain continues at the desired power level. In small reactors, the same principles apply, though the compact size demands careful attention to neutron leakage and reflection. The energy released per fission is millions of times greater than typical chemical reactions. A single uranium nucleus yields roughly 200 million electron volts when it splits. Over many events, this adds up to usable heat that can drive turbines or other systems. The process depends entirely on maintaining the right balance of neutrons, fuel, and moderation so the chain neither dies out nor runs away. Small reactors exploit these fundamentals in simplified packages. Their cores still rely on the same fission mechanics and neutron economy, only arranged for easier transport and operation. Understanding how atomic structure leads to sustained chain reactions therefore forms the starting point for every design that follows. Small reactor cores bring these neutron behaviors into sharper focus. With less material overall, every neutron counts more than it does in a large plant. Leakage becomes a primary concern because the surface area relative to the volume grows larger as dimensions shrink. Neutrons born in fission travel only a short distance before they meet the edge of the assembly. In a meter-scale core, many simply stream outward and are lost, lowering the chance that the chain reaction sustains itself. Moderation must therefore occur over reduced distances. The slowing medium, whether water, hydride, or graphite, has to sit close to the fuel so that fast neutrons lose energy before they escape. Yet the same proximity raises the risk of parasitic absorption. A moderator atom that captures rather than scatters removes a neutron that could have caused fission. Designers adjust the volume fraction of moderator to fuel until the spectrum yields the highest usable reaction rate. Small shifts in that ratio can move the core from supercritical to subcritical without any change in enrichment. Neutron economy tightens under these conditions. The effective multiplication factor must still exceed unity after leakage, absorption in structural materials, and control poisons are subtracted. Because leakage scales with surface-to-volume ratio, compact cores often require higher fissile density or neutron reflectors wrapped around the boundary. The reflector returns some escaping neutrons, yet it adds mass and changes the leakage spectrum in ways that must be modeled in detail. Fuel arrangements respond to the same pressure. Tight lattices increase the probability of fission before leakage, but they also raise local power density and complicate heat removal. Burnable absorbers and graded enrichment further trim excess reactivity at the beginning of life. Without these measures, the core would start with too many neutrons and finish with too few once fission products accumulate. The net result is a narrower operating window. Small reactors therefore depend on precise knowledge of mean free paths, resonance escape probabilities, and albedo values at every stage of the design. Those quantities, once fixed, set limits on achievable power density, cycle length, and overall system mass that larger reactors rarely encounter. Building on those Neutronics limits, heat removal in small reactors must work within tight margins. The compact core produces intense local heating, so thermal hydraulics rely on precise coolant flow paths that larger plants can ignore. Natural circulation often takes the lead here, driven by density differences that arise as water or liquid metal warms and rises. Engineers size channels and orifices so buoyancy forces alone sustain adequate cooling even after pumps coast down. This passive approach simplifies the plant, yet demands careful verification that vapor bubbles will not block flow or create hot spots. Resonance effects from the earlier neutron calculations feed directly into these thermal models because any shift in power distribution changes local temperatures and therefore coolant properties. Feedback systems close the loop between heat generation and removal. A negative temperature coefficient of reactivity provides the first line of defense. As fuel or moderator warms, neutron absorption rises and the chain reaction slows without external signals. In small designs, this coefficient must stay strongly negative across the entire operating range, since there is little excess reactivity to spare. Secondary controls, such as movable absorbers or variable coolant chemistry, trim power during normal maneuvers and protect against over-temperature excursions. Stability also depends on how quickly sensors detect changes and how the system responds. Thermocouples and neutron detectors feed data to digital controllers that adjust flow or insert absorbers within seconds. Because the core is small, transport delays remain short, allowing the feedback loop to damp oscillations before they grow. Over longer periods, fission product poisoning alters the power shape, so the same control logic must accommodate gradual shifts in heat deposition without operator intervention. Taken together, these thermal and control features keep the reactor inside its narrow safety envelope, even when external power is lost. The result is a self-regulating machine whose performance rests on the same fundamental quantities that set its size in the first place.